In May 1985, 2 fire tests on open-deck car parks were conducted at the BHP Melbourne Research Laboratories. Present fire protection requirements for steel open-deck car parks make them uncompetitive with alternative concrete structures. The tests were designed to show that it is not necessary to fire protect steelwork in open-deck car parks. The tests were conducted and planned by the AISC in conjunction with MRL and the Australian Building Regulations Coordinating Committee. 5 recent model cars were parked in a typical open-deck car park, so that the spacing between cars was about 400 millimetres. The cars were chosen as being typical of modern cars, with representative quantities of combustible materials. The petrol tank of each car was filled to 1/2 capacity. The first test was conducted on the 21st of May and was witnessed by a large group of engineers and people representing building regulatory authorities. Concrete wall panels were placed around the structure to give 50% side opening, and the upper floor of the car park was loaded with bricks to simulate the presence of 12 1.7-ton vehicles. The concrete floor slabs were cast on metal decking and contained no fire emergency reinforcement. All connections between beams and columns were simple bolted connections. The fire was started under the front seat of the test car, and the driver's window was left open to allow the fire to develop inside the car. The windows of the adjacent car were also left open to see if spread of fire was likely in this situation. After 1 minute, the windscreen of the test car shattered and flames gushed from the front of the car. The temperature of the steelwork was measured by thermocouples placed on the beams and columns, and a continuous record of fire and steel temperatures was taken. After 30 minutes, the fire had not spread to either of the adjacent cars, but the petrol in the test car was burning out of the filler pipe directly onto the exposed steel column. The test car burnt for about 70 minutes and was completely burnt out. The 4 other cars sustained only minor damage, such as bubbling of the paintwork. A second test was conducted on the 22nd of May. For this test, the car had a plastic fuel tank and a full LPG tank. The configuration of the cars in the car park was identical to that in the first test. Again, the fire was started under the front seat in the test car. After 1 minute, the windscreen broke, allowing the rate of combustion to increase markedly. After 10 minutes, the inside of the test car was completely engulfed in flames. "14 minutes after the start of the test, the LPG tank began to vent its gas to relieve the build-up in pressure due to the heating of the tank, but the vented gas did not ignite. At this time, fire spread to the adjacent car, and flames from this car impinged directly on one of the steel beams. After 30 minutes, the flames spread to the front grille of the test car and some spalling of the concrete wall panels took place. After 35 minutes, the car on the right side of the test car caught alight, and the inside of this car was completely consumed. 50 minutes after the start of the test, fire in the car on the left of the test car spread to the petrol tank, and flames from the petrol tank impinged directly on the steel beams overhead. The fires in the cars continued to burn for more than 90 minutes. The interiors of 3 cars were completely consumed, but the plastic fuel tank and its contents were not burnt. Considering the steel temperatures, it was found that the average column temperature at the hottest cross-section reached 260 degrees centigrade in the first test. In the second test, the average temperature reached only 75 degrees. It should be noted that such column temperatures are well below the limiting value of about 500 degrees, at which a fully loaded column would begin to transfer load to cooler parts of the structure. In the case of the beam temperatures, a maximum temperature of 290 degrees was obtained in the first test, while in the second test, a maximum temperature of 340 degrees was reached. Again, these values are well below the limiting value of about 600 degrees, at which a fully loaded beam would transfer load to cooler parts of the structure. After 2 tests, the car park structure showed no sign of deterioration. The beams and columns suffered no permanent deflection, and the floor slab showed no increase in deflection or cracking due to the test fires. The tests demonstrated that fire protection of steelwork in open-deck car parks is not necessary, and have provided a basis for modifications to the relevant Australian building regulations.
What exactly does happen during a fire involving cars in a closed car park constructed of unprotected steel columns and beams? How safe is that unprotected structural steel? Does the fire spread from one vehicle to others? How effective are sprinkler systems? What's the effect of the fire on the ventilation system? How high is the temperature of the air and of the steel itself? And what about the effects of smoke? It was to answer questions like these that the BHP Melbourne Research Laboratories conducted a series of extensive fire tests in a closed car park in late April, early May 1987. The tests involved regulatory authorities from several states, as well as fire brigade personnel, architects and engineers. At present, building regulations throughout Australia require that all closed car parks must use fire-resistant materials, usually with fire ratings of up to 4 hours. This means that structural steel requires costly fire protection. But in open-deck car parks, the building regulations now allow the use of unprotected structural steel. This follows tests in 1985 by the Melbourne Research Laboratories, which proved that structural steel without fire protection covering could be safely used in multi-storey open-deck car park buildings. Since then, many open car parks using the unprotected steel structure have been built or are under construction around Australia. But what about the use of unprotected steel in closed car parks? Is it safe there as well? That was the main reason for the latest fire tests, a total of 9 involving 20 cars. Each one was done inside the closed car park building, which was fitted with minimum regulation sprinkler and ventilation systems, although they were not always used. In each test, one car, designated the test car, was set alight. It was then filmed with a normal video camera until the smoke, which filled the area within minutes, made this impossible. From then on, an infrared video camera recorded each test. As you will see later, it provided the clearest record, even though the pictures are in black and white. This camera was able to trace the progress of the fire. As well as visual monitoring, air and steel temperatures were measured using thermocouples welded to the steel members. The pressure of the water at various points in the sprinkler system was also checked, as well as the smoke level through smoke meters. The concentration of toxic products was also monitored, as was the airflow in the building. The most striking observation to come from the tests was the effectiveness of the sprinklers in confining, controlling, and extinguishing the fire. Sprinklers offer the most direct and effective means of providing a very high level of safety for people, for vehicles, and for the structure itself. The key findings of the closed car park tests were: with a functioning sprinkler system, there is no need for any fire protection of the structural steelwork. Even without a sprinkler system or fire protection, structural steel is not likely to be seriously affected for at least 30 minutes. Now let's look at these closed car park tests in some more detail. The test structure used for the later series was originally built for the open deck tests. To fully enclose the building, sandwich panels of steel sheeting and 50mm insulation were placed on top of the existing precast concrete lower wall panels. In all tests except one, 5 cars were placed inside the test buildings. The cars were chosen to give quantities of combustible materials representative of recent model cars, and each test car had 40 litres of petrol in the tank. As this infrared video shows, the tests highlight the fact that the quantity of plastic material in modern cars contributes to a higher fuel load. And remember that what the infrared camera is filming is heat, not light. Those areas of white on the screen are hot spots, burning gas or metal, for example, above 300 degrees. When sprinklers were used, a situation such as this fire did not develop. But back to the car. For a start, see how the right-hand plastic rear vision mirror falls burning to the ground. As the fire gets more severe, you can see plastic material dripping from holes under the car. Next, the left-hand rear vision mirror falls and burns behind the steel column. After about 20 minutes, the left-hand tail assembly falls on the floor and begins to blaze. A few minutes later, the plastic petrol tank bursts. By now, the fire has spread to the adjacent cars, and the sounds you can hear are either tires losing pressure or glass falling to the ground. Finally, the sprinklers are turned on. Only 20 seconds after the sprinklers began operating, the fire is contained. Temperatures begin to fall dramatically, and the smoke starts to clear. Although the test building was fitted with both a sprinkler and ventilation system, they were not used in all the tests. Some tests were conducted with both the sprinklers and ventilation operating, some with sprinklers only, some ventilation only, and others no sprinklers, no ventilation. It is significant to note that the air temperature reached between 850 and 1050 degrees centigrade when the sprinklers were not used. When the sprinklers were used, the air temperature was always below 100 degrees. Now, the steel temperatures. And again, without sprinklers, the temperature rose to above 400 degrees. With sprinklers, the steel temperature remained at less than 100 degrees. So, as you can see, the sprinkler system proved to be extremely effective in containing the fire, in maintaining low temperatures, and in reducing the time for smoke to develop and for people to be exposed to any toxic fumes. The sprinklers also reduced temperatures even when they were turned on after the fire had been allowed to develop and spread. So, in summary, these tests prove conclusively that with a functioning sprinkler system, there is no need for any fire protection of the structural steelwork in closed car parks.